Alright, time for another draft physics video presentation. DraftPhysics.com and DraftScience here on YouTube, but YouTube is an evil place, so who cares? Yeah, anyway. Alright, there's a couple of comments, in this generic category of whatever, psychobabble, I would argue. But whatever. Well, the difference between engineers and scientists. So these comparisons, I don't think mean much. I think there's good scientists and then there's good engineers. And, there's good people and there's crappy people. And I think the difference is in how thoughtful they are and how honest they are. And that's about all there is. So I'd say, like in this conversation, there's just this obvious dishonesty in people in the sense that there are valid questions that have been raised in the 10 years I've been making these videos regarding the integrity of some of the beliefs of physics. Some of the conclusions they've drawn are suspect because the evidence is obviously suspect and weak, and they won't even concede those simple principles. It's not because they're engineers or they're scientists or they're this or they're that. It's because they're rotten human beings. I mean, their whole process of going through life is rotten because they're dishonest. They know should be better. They know their evidence should be. I mean, the Eddington experiment should have been repeated. Okay, it's a fundamental, classic, cornerstone of a whole theory of physics. It is the thing that gave it the theory some integrity as evidence. It was a very important experiment, and even for that reason alone, they should want to repeat it, with some sort of integrity, some sort of way that is very similar, not very abstract, radio signals, all kinds of other ways they say they've confirmed. They should want to do it the right way, the most direct way. And it's just showing how dishonest people are that they won't concede these simple arguments. And now these points I've raised about kinetic energy are valid points. The fact is the history is lousy. Okay, that Leibniz's arguments about monads and solitons was batshit insane. Okay, and then the later experiments with clay are obviously riggable. They don't have any integrity at all because just heat the clay a little bit, change things a little tiny bit, you get different answers. This is obviously not good science, and they won't even concede the point. They're saying, look, it's fine. They're convinced that the theory of reality works out better with kinetic energy in it. Fine, just admit that, and admit you don't have great reason to believe. Okay, except some sort of intuitive, I just know it's got to be true kind of thing. The scientists can't be wrong, whatever the theory is, but admit that and concede that, yeah, well, you've raised some points about the evidence being pretty lousy and pretty absent, and those are valid criticisms, and we should tighten that up. We should actually prove, with evidence, our assertions. That's what an honest person does. So it doesn't matter whether you're a scientist or an engineer. It just matters on whether you're an honest person or a dishonest person. And clearly they just want to win the argument. Clearly their despise of me is the only thing motivating some of these people, is they just want to tear me down. They want to just knock down the winner, so to speak. And that's it. They're not in this for any other, purpose. And that's really the difference. And Professor Lewin is an elitist douchebag. And that's just the fact. He's just an elitist douchebag. He's very proud of himself, very full of himself, because he gets all these accolades from a bunch of teenagers that he sometimes, molests, whatever. So some vague, hanky-panky bullshit. But anyway, so he has enough groupies to keep him thinking he's being a good scientist. And he's just regurgitating what he was taught, okay? And you see it in his experiments. They're exactly the same ones MIT did in the 50s and 60s. And he's just riding on this, elitism. Once you get on that train, you don't have to do any work anymore. Once you're known as the man, the science man, you don't do science anymore. You just pretend. you know, where the engineers daily have to get electrocuted by things, so they might have a different opinion. But I'm just saying a lot of the engineers are just as myopic, just as stubborn, just as unyielding to truth. Look how hard these guys are out there searching for their, trying to prove their ether theories, or trying to prove their flat earth theories even, or trying to, they're investing an awful lot of work, and they're attempting to get their free energy because they want the money and blah, 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 and the fame and the whatever. The whole glorification of Tesla, not conceding he was, a very flawed scientist, full of his own, stuff that just you lose credibility when you start thinking, well, I was born on midnight on Friday the 13th in a lightning storm, or whatever his whole, and therefore I have a magical life. Please. Too silly. All right, so then this other guy says, an intelligent person with nothing to do but think and no one to challenge his thoughts is a dangerous thing. So I don't think that's true. I think a lot of good science can be done in solitude without the distraction of people fucking you up, telling you it can't be true, or some other kind of thing. And so sometimes it just gets in your way. It's like having sometimes a music teacher destroys what might have been the talent of somebody to master the instrument or something, because they make them afraid, or they make them intimidated, or they do something else to just obstruct the process. So I think it works both ways. The problem with Ken Wheeler is he's a liar. Okay, that's nothing to do with an intelligent person. It just has to do with a person who's dishonest, and Ken Wheeler is dishonest. He's fundamentally, it's ingrained in him. He sees the human race as an inferior species, and they're just there to be manipulated, and he has no. His passion for the truth is a passion for a metaphysical truth, and he wants to try to force the science to fit his metaphysics. So, like Leibniz, he's a zealot, a religious zealot, essentially, and an ether zealot, and that's all. And so it has nothing to do. I mean, clearly he has been challenged, and clearly what does he do when the challenge shows up? Is he finds some way to make it go away. So it's not that he hasn't been challenged, it's that he won't allow challenge. And so that's his character flaw. So this Chicken Little said so. Kind of an obnoxious title. Anyway, it's not free energy, just the ability of the elastic medium to introduce captured energy into the equation. I'm sorry, that's still free energy. So this saying it's not free energy when it can't, it's categorically, okay, by definition. Where the hell is my chalk? Now that should not have been something I lost, but it appears I have. Alright, I'll be back. I have to go find the chalk. It was right where it was supposed to be, just under a bunch of clutter. Okay, there's probably enough light, so I'll draw a little bit of this again just to point out there's no real way to get around the problems created by having two theories of energy, momentum and kinetic energy, because the two theories don't come up with the same answer, and if you believe in one, you end up creating free momentum. If you believe in the other, you end up creating free kinetic energy, and you can't deny the facts. Okay, so the fact is, you send something in Lewin's experiment, it has a certain amount of energy. Okay, you could just say it's 100 watts or whatever you want to put it in, joules. Has a certain motion in a direction. Okay, you put it into your little experiment, and it comes out, okay, in a different shape. It doesn't matter what the shape is. Okay, so it's got a different mass and velocity, but clearly what it's got is more momentum. Okay, and you can't deny that's what the results are. So you start with 100 momentums and you end up with 130 momentums. Going that way, that's free energy. You can't get around it. It's free energy. It has a consequence. It's free energy. It's free. It's momentum. And let's understand. Let's understand. Let's emphasize and make clear, okay, that the whole thing with this collision thing is that you can't do, it's these experiments that don't work, right? You hit small thing into big thing, and small thing bounces off and a part of the energy goes this way, and the same thing happens when you hit big thing into little thing. You can't make little thing go it doesn't work. Okay, you can't put all this energy into this thing and make this thing go way faster, so you can only make it go away the same speed as it hit, and so therefore this can't get all the energy and this has to keep going. And so those are the problems, but we know that we can fix all of those with a converter. So as long as you put a converter in the system, a lever, then you can hit the lever in different locations. I can hit here, and I can put the object here, and we know that that'll increase the velocity. So I can go from, big mass, small velocity, to big velocity, small mass. I can do the conversions. So if I do the collision by putting a mechanism, a converter in between, to convert the energy, then I can do these collisions. Then I can hit big thing into small thing. And I can do small thing into big thing, because I can hit the small thing out here on the lever and put the big thing here, and I can do the same thing where I can take a high velocity and turn it into a low velocity. So a lever is essentially a mass momentum converter. So and so that's where the truth is. The truth is what happens when you do the straightforward conversion instead of some other, I have a spring in here, and then we compress the spring in the direction we're going, and then the spring releases and gives more energy. I'm just saying this, it's pretty hard to make that make sense and say it's not free energy. Of course it's free energy. If I have more momentum or kinetic energy after the experiment, and I didn't put that energy in, so I didn't do any work, there's no chemical explosion, there's no event, then you have to call it free energy. You can't play the game. Alright, it's not free energy, just the ability of the elastic medium. So he's talking about a spring, essentially, or a rubber ball. He's not talking about a hard thing. He's talking about a storage device, essentially, okay, to introduce captured energy, right, but captured through what? The same exact motion that's also going to make the object move. So you're using the energy twice, essentially. You're compressing with it in the same direction you're going. You push the object, and then you push it again with the same energy that you stored into the equation. As compression starts, the medium is transferring motion into the arrested mass. Right. And if it's transferring the motion 100%, that is all of the motion, then when the spring releases the extra 30, that's an extra 30. So I'm just saying it still ends up being free energy. Reducing the force needed by a purely kinetic force to accelerate it. So it still doesn't mean anything. A purely kinetic force to accelerate it. Reducing the need, none of that makes any sense. It stores energy, and the storage doesn't cost anything, is the point. Because the storage is against an object that's still going to move. So you're compressing the spring, you're pushing into a spring, compressing it. You're also moving the thing the spring is compressing between. And then you're releasing the spring. So you're using the energy twice. Accelerated. Plus, provided the elastic medium has not exceeded the limits to return that energy gained by pushing again off the mass once the elastic condition has ended. Yes, so you're saying exactly what I'm arguing, and yet you don't understand how, well, if you have 100 momentum going in and you have 130 coming out, that's free. 130. And I just keep doing that over and over again. I put the 130 into the same system, and now I have 160. And then I put the 160 in, and I got, two whatever. Elastic collisions capture and return energy lost in non-compressible collision. So again, just mush, absolute mush. Because we know there's the two kinds of elastic. There's the pool ball example where two hard things hit each other. And then there's this trick example where you make things super elastic by putting a spring between them. And clearly they're not the same thing. Clearly the same formula can't predict both events because clearly they're not going to be the same. The spring does change it. So you're just playing games with words as far as I can tell. Denying an undeniable truth. Alright, so the V guy. So now we'll get more elemental in the terms of the physics argument. Just to clarify, address a couple of things. I don't see why an atom... Okay, so let's understand the atom isn't the elemental bit. So the atom does what the electrons and protons do. The electrons and protons are the objects being motivated. The atom is motivated not at all. There's no such thing, essentially, as the atom. There's just the electrons and the protons, and whatever the electrons and protons are compelled to do is what the atom does. All right. With a bias in a direction, going 30 miles per hour would have any issues getting hit by even more force, constructively adding to the velocity. So let's go back to there's different ways to understand how motion happens. And what I've argued is that force really does have to push matter. It doesn't get to just push it and then say, I'm done. So the idea would be is this was an electron and a piece of force is going to hit it. It doesn't just hit it, bounce off, okay, and this goes this way. That's not conservation of energy because you have two things moving now. You have the electron moving this way and you have the force moving this way. So that's not very conservational. And what I'm arguing is that the real truth is that the force has to actually keep pushing the object. It has to push it, push it, push it, push it, push it. Okay, it has to stick to it and keep pushing it, keep pushing it, keep pushing it. So it was going the speed of light. While it's pushing, it's going 1/10 of the speed of light or whatever. Pick a number. And so this object can only go the reduced speed of the tiny force hitting the heavy object. And it isn't until some other counter force hits, then the force reflects, this force reflects, so you still have those forces are balanced, and this one stops. But it doesn't stop if it has, say, for example, a gamma ray behind it. So if we have a gamma ray behind it, that means that we basically have a bunch of force behind it. So when another force comes in, only one of these reflects. And so then it can keep pushing. And then another one can hit, and then another one will reflect off, and this one will reflect off, and this one will reflect off. So it has to hit a lot of stuff before it loses that. Now the trick is that while all this is happening, the universe is also pushing energy in other directions. So when you're doing this thing, you're trying to get a bias in this direction, you're also getting hit this way and this way. So you're constantly jiggling this way and this way as you're going this way and this way. So the very idea that you could ever get this object up to the speed of light is pretty impossible, because any motion in this direction is not going to be a motion in that direction. So you know that you can't move the speed of light this way if you have to do this motion. You can't do this motion at the speed of light. Right? If you have to do this and this and this and this and this and this, you can't possibly, you can do this motion very fast, but you can't get from here to here at the speed of light. So the fact is that there's other things limiting how fast you can go. You can never get all the fish pointed in this direction, because all the fish are never even if you imbalance the force here from 0 to infinity, okay, even if you have an infinite amount of force pushing and you have 0 force coming this way, which is pretty much impossible, you still have this and this. They're going to constantly change fish, constantly make them go wrong ways. So you're going to constantly have to clean up the mess being made by the jitter in these other directions. So you're never going to be able to achieve your speed of light. So there's like 3 reasons it gets harder to push things once they're accelerating. The fact is that it's harder to hit things that are not going the right way because there's less of it, so more of your energy goes through without hitting anything. And the faster you're going, and you have all this jitter to get over, and you're not going to have a field where there's no opposing force. So anyway, just to clarify, I mean, it's this stuff I have talked about in the past, so if you don't know the context, it's going to mean little to you, I suppose, but whatever. All right, I can imagine, however, that hitting atoms, okay, so it's the bits of atoms, right, you clarified, so you never hit an atom, you only can hit electrons and protons, so there is no, the interactions are always going to be complex in the sense that if an atom's moving, you had to hit it with more than one little piece of energy, because you can't motivate the whole atom by just hitting the electron. You've got to do more than that. With a bias in an opposite direction would require some more force to be wasted during the non-constructive interactions. Alright, however, I can imagine that hitting atom bits of atoms with a bias in the opposite direction would require some more force to be wasted during the non-constructive interactions. I don't know what that means. I think all the interactions are constructive. The problem is having the interaction is sometimes, like again, if I'm moving away from you very fast, it's hard for me to have interactions with the field that can't catch me. Can't catch me as much. This kind of gives me the clear idea of why the force would be wasted in these scenarios. But I hear your point. You see it differently. Yeah, I don't understand exactly what your point is, so I can't really say much about it. I'm just saying that if we use the school of fish analogy, and the idea is you're sending plankton in, and the plankton moves the fish, some way to, analogize it. I don't know how exactly to make a perfect analogy. You could even say there's fish, and the fish hit the fish and straighten their direction. A fish is going this way, gets hit this way, goes this way. The fish in the school. And so you're just changing the direction of the fish. You can just sort of understand that, yes, it's more complicated because it's in the ocean and there's fish coming from all kinds of directions. So a bias in this direction will exist, but it's going to be weakened by the fact that there has to be a lot of other motions that will dilute that bias. So achieving a high velocity is not very likely for a piece of matter. The Leibniz comment was sort of a joke because I loosely connected. So he said that Leibniz ruined Einstein's theory somehow would have been okay if it wasn't for Leibniz screwing it up or something. Because loosely connected kinetic energy and gravity. Because I loosely connected kinetic energy and gravity. I just can't. There's no way I can't loosely connect kinetic energy. I'm just saying, for me personally, there's no connection, and clearly gravity is the whole reason this kinetic energy thing exists, because gravity isn't a constant force in the sense that it's going to apply a completely different force to this object than to me. I mean, I have a 100-pound object, it collects much more gravity than this will collect if it's falling, and that's why they fall at the same rate, is because gravity gives a tiny amount of energy to this and it gives a gigantic amount of energy to the heavier thing, and people are thinking of it as the same force, and it's variable, completely variable to your mass. Your mass is how big your sail is. How big your sail is decides how much wind you collect. How much wind you collect decides how much energy you have. And then how big your boat is will decide how fast your boat's going to go, with the amount of energy it's collected. All right, Einstein with his bent space. Yeah, a big boat with a big sail is going to be the same thing as a little boat with a little sail. The same wind will push both of them the same speed. All right. Leibniz was closer to a better answer than Einstein. See this? I just can't understand why you'd say this after all these videos. So just by pushing the kinetic energy, Leibniz was closer to a better answer than Einstein with his bent space. They're both really bad theories, frankly. Squaring velocity, a really bad theory, and bending space is vacuous mush. It doesn't say anything about what's moving the electron. It just says, oh, the electron knows the space is. Electrons can read space bent. How do they read that? How do they see the bent space? I mean, it's just too silly. Bent space being infinitely far from a real mechanical answer. Yes, but they're both wrong, bad theories in my opinion, poorly evidenced and just not very reasonable or logical. I have another bit to add on kinetic energy and why it could be more of a representation of useful work. So again, this notion, again, all it really comes down to is that velocity thing. That velocity requires, it's like the difference in light. It's easy to make a light source that shines light in all directions. It's hard to make a light source that shoots light in one direction. I would say hard, but it's more difficult. And it's true of nature, and it's true of our common experience. So things with a high velocity require a more complex environment, a creation event that's more complicated than creating light in all directions. It's that simple. The gun is more complicated than just blowing up a piece of dynamite. I have another bit. Okay, so useful energy, but I'll think it over maybe for another comment. Oh, sorry. And yeah, it would be nice to see some experiments. As you keep saying, it's kind of unbelievable that some of these basic experiments can't be found on the internet. It's just ironic that they have a definition for what a joule is. A joule is lifting 100 grams, 1 meter. And we all know that the work lifting is exactly the same work gravity will do falling. So they're both the same thing. The lifting is against gravity. Gravity produces the same force dropping it. So we know that it's just 100 grams falling 1 meter is a joule. And so it's just amazing that they've never dropped 100 grams and seen how much it weighed. I mean, it's just so obvious a definition of what a joule is. It's a weight. Weights are created by forces. You don't have any weight. You're in the middle of the space and there's no planets and stuff. You obviously still are being influenced. You have some gravitational weight to the solar system, but I just mean if you could be in an empty universe and you're just sitting there, you have no weight. I mean, I can't put a scale next to you and have you can't, you're not moving. There's no momentum. And it's momentum that creates weight. You have to have a velocity to have a weight. And the way we weigh things is based on a velocity acquired based on your mass. And that's exactly what gravity does. Gravity gives you a weight or a momentum that you acquire based on your mass. The more massive you are, the more force, the more weight. But you're going to collect equal amounts proportional to your mass. And so that's why it works as a way of weighing things and then saying, well, there must be this much mass because it moved this much. And the only way it can work is that the force had to give you the momentum. and it gave you the momentum proportional to your mass. So you can just measure the momentum to measure how many atoms you have and how many electrons you have, because they're the things that got moved. All right, wait. And yeah, it'd be nice to see some experiments. And as I keep saying, it's kind of unbelievable that some of these basic experiments can't be found on the internet. Hopefully someone links one at some point. I have to find one first. So, let's see. There was some chitter-chatter among the peoples. So, I don't know. Observe 45er. I don't know what that means. Yes, I will accelerate. Yes, it will accelerate either way. So, he's arguing that it doesn't matter how fast you're going, you're still just as easy to push. And I'm arguing essentially that the pushing force is a lot less effective the faster you're going, because you're effectively getting transparent. So just like my analogy of the, if I could move something away from you at, half the speed of light, and you could understand how less reflections would be happening off the object, less stuff could bounce off of it and go back to you. And so it would get dimmer and dimmer. The faster it goes, the less material it becomes to you, an observer, from behind, from the way the opposite direction it's moving. The same thing is true for a force you're going to apply to it. So just like you can't get the light to reflect off the object anymore, you couldn't get a force to be able to hit the object with the same effectiveness. So you'd have to shine a brighter and brighter light to get the same reflected light back. And the reflection is sort of an indication of effectively pushing. So you can just sort of understand that it will be harder and harder to push it as it's going faster and faster. And the fact that less light would reflect off of it is an indication of the fact that you'd be harder to hit things. It's hard to hit the little bits because they're all moving away from you, and there's less chance of you hitting them effectively. Okay, and so he says, and by acceleration I mean the true meaning of change velocity. Is there some other meaning? The problem with the word acceleration is that they always think it has to be per second or per hour or per day or per a unit, when it could just be the acceleration over the entire process, the entire time of the experiment, the entire time of the change in acceleration. And if you make that the unit, then you just have force equals change in momentum. Anyway, it isn't any harder to accelerate it. It is already moving if it's already moving. So you're saying so, but you won't be able to demonstrate it. So, and I'm saying I can logically model why it's more difficult. I don't know if you can logically model why it would be the same. That's what he appears to be saying, and if so, he's mistaken. So he's saying I'm appearing to say it is harder. It isn't any harder. I didn't say it isn't any harder. So that's not my position. So I don't know whether that's poorly written or what. But we'll see. If a force is applied to some mass that acts for a time, so again, they're just obsessed with fiddling with time, and I think that's supposed to be it, time t, okay, for a time t and accelerates it from 0 to 5 miles an hour, then that same mass traveling at 30 miles an hour will accelerate to 35. Says you. I'm just saying that these experiments we can't see the difference at those low speeds, and obviously, so, it's an open question in terms of an experiment. If that same force is applied for the same time in the direction of travel. So I think it does, you can say it doesn't matter, whether it's an opposing force or this force. I think it does matter. It's easier to hit something that's coming towards you because it's becoming more and more opaque. So but anyway, If that same force is applied for the same time opposite to the direction of travel, it will cease to negate acceleration. It will cause a negative acceleration to the speed of 25. So again, you're just restating the same principle as if you've got some proof, and you don't. I mean, like I said, none of these effects can be seen at these slow speeds. These are nuclear effects. Anyway, in addition, if the same force is applied sideways, perpendicular to the direction of travel, it will gain a sideways component of 5 miles an hour, leaving the forward component unchanged. Yeah, that's only if you believe that it can go sideways, actually move sideways and move this direction at the same time. And it can't. It can only go one vector, so it can only do this, and then have to do this, and then have to do this, and then have to do this. And you can't really argue that that's not a substantial difference in its velocity. The basketball player has a velocity. The basketball has a much higher velocity, technically in this direction, in the sense that it's obviously the ball is traveling a much faster to be able to do all that zigzagging while the player's going this way. Just a fact, frankly. In addition, if that same force is applied sideways, perpendicular to the leaving it unchanged, the new velocity is the vector sum of 30 and 5. This is 30.414 miles per hour, or degrees off the original path. This kind of thing is explained in many tutorials on the net. So again, more mush about your tutorials and your math, and you don't have any experimental evidence, so that's the real problem. And again, you can't do incredibly low velocity experiments and say you're getting to the nuclear function, because you really aren't. What's happening to the electrons and protons. Alright, so V says, we're zooming into atomic and subatomic realm and theorizing about mechanics of why there would be a bias for velocity. Why or why not kinetic energy and its ability to do work rose exponentially with velocity versus momentum. Yeah, I don't think the two subjects are all that related, frankly. I don't think in any way you can explain why velocity increases energy by itself, in and of itself. Absent the mass component. I mean, I don't think there's any rational way to show me mv squared. I don't think there's any way for you to show how mv squared works mechanically. That somehow velocity, just because you have smaller mass and a higher velocity, that you now can impart more energy. And I guess the lever example, it demonstrates it for me. You hit the lever with your small mass and your high velocity. The lever does this, and it gives a high torque, a high torque, so it can push a heavy mass at a slower velocity. But you're going to get the same in and the same out. You can't say the thing that left, I mean, this is just so elemental. I mean, this is the kind of experiment we need to have done, right? This is so simple. I mean, it's just so simple. So yeah, just make a lever. So, maybe I can, the guy is, the aerosol breeze guy is communicating. It's a little bit of time lag in getting anything done. So the idea is you just have a lever, and you just change where on the lever you're going to hit things and where you're going to place things. So if I place the 2 mass here, okay, so I have the 2 mass object here, and I send in the 1 mass object up here, twice the distance. Okay, so this is twice the distance. And it's got twice the velocity. Now it has a 2 velocity, let's just say. The idea is that it will go in. Okay, now this has technically got twice as much kinetic energy, 2x the KE. Alright. And what they're going to say to you is that somehow when this goes into the lever, this will come out 1.4, okay, of this velocity. Now, do you really think that's physically possible? That somehow this part of the lever can move it, you know, this to velocity, and that somehow this part of the lever is only going to convert that to 1.4. It's not going to come out twice the velocity? Yeah, come on. It's only going to go 0.4 faster. It'd have to be a pretty dull lever. I mean, it'd have to have a pretty bad bearing, in my opinion. But I'm just saying, in principle, that's the understanding. And to sit there and say that somehow this energy thing, this kinetic energy thing, somehow will convert its velocity into this thing in some, you know, kinetic energy way. I don't even know what that would be. You know, and that somehow I'm going to lose energy. You know, that somehow it's going to, the simple lever is going to somehow destroy, you know, 0.6. You know, it's somehow going to wipe out, you know, whatever that comes out to, a third of the energy. It's going to just be killed, destroyed. And, you know, heat, fires, explosions. There really isn't going to be any of those things. You know, you know, this is like dropping the weight on the train. I mean, you know that when you drop the extra weight on the rolling train, you know, to double its weight, you did motion in this direction, which is irrelevant. Causes a little tiny extra friction on the track, but it's a tiny loss. Not half the energy. You didn't lose half the energy. Come on. Just doesn't fit. So yes, until we have an experiment, all this conversation is a little bit round and round. I'm saying I don't see any logic in it. I can't see mechanically how, again, momentum is such an obvious package of energy it draws for you. It's just saying that, you know, you just make your velocity and mass. You just have, you know, it doesn't matter whether you go this way or that way. You're making a shape, a volume, velocity times mass, and you make a volume, a square. That's all you need. And all you know is that, yeah, I can just change the shape. I can make it fatter. I can make this. I can change the shape, but the volume of energy always stays the same. I mean, that's such an obvious mechanical model. It's so simple. It should be the default until proven otherwise, not merely suggested otherwise. And the suggestion is, again, the other guy's comment is completely blown up in the sense that, quite obviously, if you apply a force while something's already moving, and I apply the force, I'll get so much more energy out of the same fuel. So if I burn the rocket fuel when the rocket's going 30 miles an hour, I get a certain amount of boost in energy. But if I burn it when the rocket's going 120 miles an hour, I'll get 4 times as much energy out of it. I'll get 4 times as much boost in velocity. That doesn't make any sense. Alright, so I think that's enough. Enough of a video, I'd say. Oh, sorry. Yeah, a little obstruction. All this is so many little details, and yes, I mess up on some of the little details. Because, you know, there's so much to do. Blah, 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 blah. So, I don't know if there's any other news. Working on things. I just, you know, I got, yeah, lots of distractions, lots of things. So, you know, every day is full of things to do, and I just haven't gotten to, you know, experiments yet. So who knows? I'm again just, you know, I'm procrastinating because I'm just really hoping there is a link somewhere on the internet, and there is somebody willing to do the simple lever experiment, for example, weighing the stick of butter. There's somebody willing to do it, and I don't have to. All right. Anyway. So, yeah. So, yeah, we'll call it a video. And yeah, there's just nothing. There's nothing. Just nothing to respond to. There's just nobody's making interesting videos, in my opinion. So, except for me. Yeah. So, till the next time and such. So forth and whatnot. This has been a draft physics video presentation and such.